All right, following up from our example in this section, I want to talk about a very useful technique called regularization, which can be used, among other things, for model or feature selection. So, just to recap where we were in our example, we were looking at predicting housing prices, and after we did a little bit of cleanup of the data, we had a data set that basically had 174 variables associated with each record. So there were a large number of these variables, and the basic question we wanted to ask was we needed to really identify which of these variables or parameters really mattered. There were two reasons we wanted to do that. One was just to better interpret the results, but also if you go back to the previous unit, you know that if you can reduce the number of variables in your model, you will improve the generalization error. Now, one key idea in model selection is the concept of sparsity. And to understand that, let's just consider any linear model. For example, like predicting the price of a house. A linear model, you have that the target is a linear sum of these variables. Now, if one of these coefficients, say beta j, is 0, that means that variable is essentially being ignored. It means that it's not being used in the prediction. So if I want a model that uses very few variables, it's equivalent to asking for a model where most of the coefficients are 0. In that case, that is called a sparse coefficient vector, and we want some way to ask when we perform the fitting to get a sparse solution. The technique behind this is called regularization. So regularization actually applies very generally, and it's a general method for finding solutions with some constraints. For example, if I want to have solutions that are sparse, but we'll look at other types of constraints too. And just to make it more concrete, let's go back and look at our least squares problem. In the least squares problem, in general, in the unregularized form, we're trying to minimize the mean squared error, which is just the sum or the average of the squared differences between the predicted and true values. Regularized estimator does the same thing but adds a term. So instead of trying to minimize the mean squared error directly, you minimize this function, which I've called j, and it has two terms. One is the mean squared error, just like before, but I also have this other term which I've called phi of beta, and that's called the regularizing function. And the concept is that you try to select this regularizer to penalize values of beta that are unlikely or undesirable in some way, and try to favor solutions of beta to what I want. For example, solutions that are sparse. Now, there are two types of regularizers that we'll focus on most in this class. The first is called ridge regression. It has a term which I won't go into the explanation, and it's defined as some scaling times the sum of the squares of the coefficients. And the second one is called LASSO, or called L1, and it's the sum of the absolute values with some scaling. Now, just to understand this, I've drawn on the right what these regularization functions look like for each particular coefficient. So the blue is the ridge regression one, and the red is the LASSO or L1 term. Now what you can see is that in both cases they put no penalty when they're 0. But when it goes away from 0, either to the left or right, that penalty grows. Now since you're trying to minimize the MSE plus this function, it will try to favor solutions in both cases that are smaller. So it tries to make it small. But there is a key difference. One is related with sparsity and the other is not, and I'll get to that momentarily. Just one thing before I go ahead is that you notice, or actually there's two things I want to point out. First is this odd scaling here. In one case, there's a scaling term, alpha, here, and is divided by n. The alpha tells you how much regularization you're going to impose. That is how strongly you're going to impose this constraint. And you see this alpha term in actually both of them. You also see this scaling here dividing by n in the L2 case and multiplying by 2 in the L1 case. This is not consistent. I just simply picked this because this is the scaling that is used in the sklearn Python package. But there's nothing magical about that. You could do everything with different scalings. All right, that's what this alpha term is. The other little minor thing that you might notice, if you were looking very carefully, you would have seen that the sum goes from j equals 1 to d. The beta 0 term is not included, and that is intentional. In general, you do not want to regularize the bias term because it's kind of related to the average value of y, and you want to leave that unconstrained. Okay. One more thing that I want to point out is that both the ridge and lasso regularizers are often written with what are called vector norms. So let's start with looking at the ridge cost function. In the ridge cost function, you have the RSS plus this squared sum of squared terms. And that sum of squared terms can be written with this notation here, which just means the vector norm. And it's written with this 2 norm squared, which just means this term here. And similarly, in the lasso cost function, you have the MSE plus this term, and this, which is the sum of absolute values, is just written like that. And this is called the L1 norm. And this here is called the L2 norm squared. Just again, let me point out there's a difference in convention with the scaling in front of these terms that is not consistent across different textbooks, but it's just I'm using the convention that is in the sklearn package. Okay. I said earlier that both the L1 and L2 regression solutions tend to select values of beta that are smaller. But there's an important difference, which is related back to sparsity. So in the L2 case, you tend to get a lot of coefficients that are small, but it doesn't get coefficients that are ever exactly 0. And that's not ideal for feature selection because you don't really know when to discard the variable. On the other hand, the L1 solution tends to pick more sparse solutions. So it tries to find coefficients that are exactly 0. And if you want a geometric interpretation for that, here's a couple of pictures that try to illustrate this idea. So in this case, in both pictures, imagine that you're on a linear constraint. And in one case, you're trying to find the minimum L1 norm, and the other case, you're trying to find the minimum L2 norm to hit that constraint. The L2 norm is the Euclidean distance from the origin. So the circle is the ring of, the contour of all these points are at the same L2 distance. So what that will mean is that you're really trying to find the smallest circle that can intersect with this line. And in that case, you would end up at this point here. On the other hand, the L1 norm is the sum of the absolute values. So its contours are actually diamonds like this. And in this case, you would want the smallest diamond that hits this. Now, what you see is that in the L2 case, you end up hitting it here, where both coefficients are positive. But in this case, in the L1 case, you only hit it here, where one of them is non-zero and the other is exactly zero. Now, this is just a two-dimensional example, but it turns out in general that this is true, that the L1 solution tends to get coefficients that are exactly zero. All right, a couple more things I want to talk about is I said that in both cases, whether you're using L2 or L1 or any regularization, you have to solve this minimization. Let's first look at how you solve the ridge regression minimization. In the ridge regression, you want to minimize this cost function, which is the mean squared error, or the RSS actually, plus alpha times the L2 norm squared. You can show, and we'll just do this in homework, that there's an explicit solution for this, which is just given by this formula here. And if you recall, this is exactly the same formula as what happens in the least squares solution, excepting that you've just added this plus alpha I term into the first term here. So you can explicitly solve this, and it's not a problem. And we'll also show that sklearn has just a routine to do this for you. All right, now let's turn to how we would solve the minimization for the LASSO regression problem. If you recall, the LASSO regression problem, we're trying to minimize the mean squared error plus this L1 norm term, which you can write in vector form like this. The problem here is that the derivative of this term is not continuous. So there's actually no closed form solution, or at least not one you can take by setting the derivative equal to zero, like what you can do for the ridge regression. But it turns out there are many solutions to methods to solve this iteratively. So an iterative method, and we're going to talk about this a lot in Unit 7, you start with some initial value for beta, and you keep on iterating, getting closer and closer to the minimum of this. And I've written some of those methods here. We're not going to talk about this type of minimization, particularly what's called non-smooth minimization, at all in this class, but we do teach in the ECE department a great optimization class. So if you're interested in that, go ahead and take that and you will learn more about it. There's a couple more little details that you need to understand to get regularization to work. And one of them is called data scaling. What you want to do anytime you're using regularization is to do some kind of scaling to put all the coefficients, all the features in the same range. So for example, you can standardize them by subtracting the mean and dividing by the standard deviation. And as you'll see in a homework, once you have the coefficients for the features in this standardized model, you can always go back and get the features in the original model. And the reason is that if you don't apply scaling, the regularization will depend on the data range. So for example, if you had one coefficient that was very large, let's say a housing price, which could be in the hundreds of thousands of dollars, and you had another variable like number of bedrooms, which maybe is like between 1 and 4, then if you start to regularize these without scaling, the housing price will dominate, and the regularization would have very little effect on the number of bedrooms. So you need to put them in the same scale for it to work at all. So that's a super important practical point to get things to work. And we're going to see that in the demo. final thing is, how do we select this regularization level? So if you saw, both of the regularizers in the L1 and the L2 case had this alpha, and greater alpha meant it was more regularized and less alpha was less regularized. So one way to think about that is that if I have a higher alpha, I'm constraining those solutions more. And so I'm in some sense picking a simpler model. So for example, if I was using L1 regularization and I picked a higher alpha, I'd be asking the solver to find me a solution that has less number of non-zero coefficients. So conversely, if you have a lower alpha, you have a more complex model. Now this might sound familiar because it's really exactly what we were doing kind of with model order, or sort of the inverse of model order. Higher alpha means a simpler model, which is kind of like having a lower model order. And lower alpha is the opposite. And how did we decide model order? Well, we use cross-validation. So we can do the exact same here. So a very simple sort of pseudocode is I would split it into training and test. For every alpha in some range, I would find the coefficients fitting the data with this alpha parameter for the regularization. Then I would look at the test data, make the predictions, and then somehow compare the test and the predicted values on that test data. And then I would go ahead and find the alpha which had the highest test score. It's exactly what we did with model validation. So let me just wrap up with a little bit of a summary here. We at least looked at 3 types of regularizers. One is to not have any regularization, and that just leaves your parameters unconstrained. And in the case when you're regularizing with the mean squared error like this, your solution would just be the standard least squares solution that we talked a lot about in Unit 3. Ridge regression has a regularizer like this, and it tries to make the parameters small, meaning close to 0 but not exactly 0. And we showed you how to solve that solution when you try to minimize the regularized cost. LASSO has this L1 norm, and it has the property that it tries to make at least many of the coefficients exactly 0. There's no analytic solution, but you can run an optimizer to do this. And again, all of these, first of all, you want to scale the data before training. And secondly, all of these regularizers have scaling factors associated with them, and you want to find them by cross-validation. So in the next video, I'm going to take these principles and return back to the housing data set. But before we do this, I want you to try to do this little, very simple in-class exercise on the GitHub site, just to pick some simple regularizers and make sure you understand the concepts. And then we'll dive back in to that housing data set.